Welcome to lesson 23, where we're going to talk about or introduce hypothesis testing, which is a very important concept in statistics. There are a number of different hypothesis tests and whatnot, but the idea behind hypothesis tests is getting at, with some level of certainty, an answer to a yes or no question. So we're going to start with the basics, introduce what we mean by hypotheses, and then go from there. So what we were looking at in the previous lessons, we wanted to know more about a parameter value. Like, hey, what is the mean OSU student tuition cost for spring 2020? So your goal is to estimate the value of this parameter. So what we're going to do, it's an estimation problem. We're going to use point estimates and interval estimates, or confidence intervals. Another type of question we could ask is, maybe we have a claim or a guess and we want to test it. Generally, these will come in the form of a yes or no question. So our goal is to test the validity of a statement. So this will be a hypothesis test. So when you have a hypothesis test, you have your hypotheses, you calculate a test statistic and a p-value. So for example, if I want to use a hypothesis tests, you want to test average ride time against an advertised time. So you might say, hey, is it the same as what is advertised? Is it longer than what's advertised? Shorter, etc. Test the proportion of defective parts in a process against what's advertised. Or in a lot of quality control, they say, hey, we can't have any higher than a certain set proportion of parts that are defective, and so you want to test to make sure it's not above that. You might want to compare tensile strength between machines, etc. You might want to say, hey, is the average tensile strength different between the machines? That kind of idea. So this is the example. We're pretty much going to work this example through lessons 23 through 25. We have a high-speed train in Italy, and it goes between Rome and Florence. Here's a little map. I don't know, it doesn't mean a whole lot to me. I've never taken that train. So the website for this company, they advertise that the trip takes 94 minutes. And we say, okay, the train website states that train times vary on average about 10 minutes. Vary on average, and it coming from the overall website, they're giving us a sigma value, or a standard deviation. Now here's where it gets interesting. We have a rider that takes this train to work all the time, and they find that they don't believe it's 94 minutes. They feel like they're late. So they go ahead, they randomly select 25 ride times. I'm not sure what kind of time of the days that looks like. And when they take those 25 random rides, the average trip time for that sample is 99 minutes. So the question that they want to get at, or question of interest, if the advertised time is 94 minutes like it's claimed, what are the chances that I take a random sample of 25 and it's 95 minutes or higher, or sorry, 99 minutes or higher? So we want to basically ask, how weird is what we saw, or weirder than what we saw, considering like if we assume that the website's correct. Okay, just like the confidence interval estimation problems, there are some standard steps that we are going to follow when solving a hypothesis test. We're going to state our question of interest, just like with the estimation problems. For hypothesis tests, this is generally expressed like as a yes or no question. So you might say, hey, is the average train time between Florence and Rome longer than what's claimed? And you put the number. Step 2 is going to be identical. We want to know what our parameter of interest is, and we're going to take inventory from the information that we have in the prompt. So we want to know if we're comparing, is it one population, two, or more? Just know that at least through this week, we're going to stick to one we're going to introduce 2 next week. So type of variable, once again, if it's categorical, go with proportions, which will be a p. If it's quantitative, we're usually going to look at the mean, so mu. So I know that it went a tiny bit out there. Choose a significance level. So we're going to talk about what this means at a later slide, but it's going to basically be saying, hey, choose a threshold. If our evidence is so strong or whatnot compared to this threshold, we're going to change our mind here. We're going to state our hypotheses, and this step is the step that this particular lesson is going to focus on. We're going to talk about stating the hypotheses. 5, check the conditions for the test. So they're going to be really similar to checking the conditions for doing the confidence interval. So was it a random sample? Can we count on the central limit theorem kicking in for the sampling distribution of x bar? AKA, is n going to be big enough? And for this week, if we want to use z methods, we want to know, hey, do we know the population standard deviation sigma? If we do, go ahead and proceed. If we don't, there are other options that we can do. Then we calculate a test statistic and p-value. And then once we've gotten here, it's very similar to the estimation problem. We have to write it up formally. We have to actually come back to the question and answer it. So return to your question of interest and describe your results. And just a note here, it's common to do both. If you're asking the yes or no question like, hey, does it take longer on average than the advertised 94 minutes for all the trains to go between Rome and Florence? If you were to respond, yes, it does appear that way, the automatic follow-up will be like, okay, well, how much more? Like, what do you estimate the average is? So a lot of times we will calculate, we will do a hypothesis test as well as a confidence interval. So the hypotheses, there are going to be 2 types. So we're going to have the null hypothesis. So the null is the boring one. It is the established claim. So we're just going to assume that the claim or statement is true. We're always going to start out believing it's true. It's always going to have an equal sign in it. As far as this class goes, we will always have an equal sign. We're setting it up hoping that we can reject it. It's usually what we don't want to be true. And then we go ahead, we denote it, it's an H, and this is a sub-0 or not. Like not means nothing, so 0, it's the default. Then there's the alternative. This alternative hypothesis usually is related to what we're interested in finding. Do we think the average is higher than some claimed amount? Do we think it's different than? That kind of idea. So it's going to contradict the null hypothesis. Not only that, it's going to contradict in a way that only one of them could be true at a time. That's what it's going to come down to. We can have one-sided or two-sided alternatives, and we'll discuss what that means. And I'm going to try and consistently denote it HA. Note that it's not very important that the A is capitalized. A lot of people will use a lowercase a or H1, like H0, H1. So as long as you use one of these 3 notations, we know what they are, that should be okay. I personally am going to try and stick to H subcapital A. So that phrase, the null is dull, it's pretty much, it's stating the claim statement. It's, if nothing interesting is going on, the null is what is true. The alternative is usually what we're interested in. So if we want to look at the train example, my null, so the train example, X is travel time, of train. So I'm interested in the mean of X. And we're just going to say, okay, it's equal to the claimed value. So the website claimed 94 minutes. And note, I am including the units. If there are units, you should include them. My alternative, I am going to set it up very, very similarly. The only thing that's going to change is the sign. And the sign is going to reflect what we suspect. So it comes down to the commuter believes that it actually takes longer. So we think that the average is higher than 94 minutes. So these would be my hypotheses for the train example. So a couple notes about hypotheses. You need to state them before you ideally collect data, but definitely before you look at it. It is absolutely cheating, like watching a race and then placing your bets, if you look at the data before you write up your hypotheses. So do not look at the data before you write your hypotheses. It is cheating. We call it data snooping. They will always be about what's going on in the population, so they should always have parameters like mu. We're not going to usually do tests for sigma. You can, but we won't. Or p. They will not ever have hats in them. They will never have X bars in them. We will hone in right there. Like the hypothesis should never have values that come from the sample. So it shouldn't have X bar and it shouldn't have that 99 minutes. It should never include those. And so then we're using sample from our data to help make a decision. So what we're ultimately doing is trying to say, hey, we're starting out assuming the null is true. Based on how weird or not weird what we saw in our sample is, if the null is true, how comfortable are we rejecting the null and saying we actually believe the alternative? So talking about this comfortableness, comfort, I think that would probably be better, was saying that the alternative is more likely true. We need to start by assuming that the null is true and then reject it. Although note, we may not always get strong enough evidence to reject it. It's just more of like a hopeful. Okay, so I promised a couple of slides ago we were going to talk about one-sided and two-sided alternatives. So we'll give you a little info on what that means. So one-sided, that's the scenario where the first one is saying, hey, I think maybe the average of the population is less than an amount. So you're using a less than sign, and when you look through the question prompt, look for less than, at most, fewer than, words that indicate that you're looking at something being lower, maybe lower than, that kind of idea. Like our train example, it's set up to say, oh, well, we believe that the parameter is greater than some value. So you'll see greater than, at most, more than. There are a lot of examples, but you're going to look for language that indicates that you are concerned that the average is higher. So yeah, you could have higher than as well. And then two-sided alternative, it's not specific in one direction or the other. So you want to know if the parameter is different than some claimed amount. Is it different than? Does it differ from? Is it not equal to? Is it other than some value? So this is the scenario where you do not have a suspicion one direction or the other, but you maybe want to find out, hey, is it different than what's advertised? That kind of idea. And when you're writing all of these should come from the question prompt. You shouldn't look at the data first and then decide your hypotheses. You should be getting whatever sign goes in your alternative from the question prompt itself. It should give you all the information you need to be able to write, which if it's one-sided or two-sided. So we have a few examples. This is an excellent time to go ahead, and I'm going to even fill them all out, to press pause. Go through these and then check them. Definitely good to get practice. So the first one, the average time to finish a maze is not equal to 16 minutes. What we want to know is this one-sided or two-sided alternative? Okay, so if I want to answer this question, I'm going to hone into the is not equal to. That is going to make this a two-sided alternative. Then we have the average running pace is less than 7 miles per hour. Tell you what, if you're talking about my running, it's a lot less than 7 miles per hour. So the words I hone in on this sentence is less than. So I'm only interested if it's lower than the 7 miles per hour. So it's going to be one-sided. The third, the average weight loss is more than 15 pounds. Probably should write this word out, not use the abbreviations. So I'm going to look at is more than. This is going to be one-sided because I'm only interested in finding out if it's higher than 15 pounds. Not interested at whatsoever in if it's lower. The fourth, the average IQ of OSU students is greater than 119. I want to know if it's higher. That's a one-sided alternative. The average exam score is different than 75%. It's different than, it could be higher, it could be lower, it could be either. So we're looking at a two-sided alternative. And then our last one, the average lunch break is fewer than 30 minutes. It's definitely fewer than 90. And tell you what, when I worked back at Target, that was the case sometimes, fewer than 30. So we're only interested in the case where it's lower than 30. We don't care if it's higher here. So this will be a one-sided. Okay, so that was our lesson. So in our next lesson, lesson 24, we're going to move on to calculating test statistics and calculating p-values that are going to help us make a decision about the hypotheses we just made.